Overview of the TCP/IP networking model. The TCP/IP model both defines and references a large collection of protocols that allow computers to communicate. To define a protocol, TCP/IP uses documents called Request for Comments (RFC). You can find those RFCs using any online search engine. The TCP model also avoids repeating works already done by some older standards body on vendors' consortiums by simply referring to a standard of protocols created by those groups. For example, the Institute of Electrical and Electronic Engineers (IEEE) defines Ethernet LANs. The TCP/IP model does not define Ethernet in RFCs or refers to IEEE Ethernet as an option. The TCP/IP model creates a set of rules that allows users to take a computer or mobile device out of the box, plug in all device cables, turn it on, and connect to and use the network. You can use a web browser to connect your favorite website, use any app, and it all works how? Well, the also the computer implements part of the TCP/IP models. The Ethernet card or wireless LAN card built into the computer implements some LAN standard referenced by the TCP/IP model. In short, the vendors that create the hardware and software implement TCP/IP. To help people understand a network model, each model breaks the functions into a small number of categories called layers. Each layer includes protocols and standards that relate that category of functions, as shown in figure. TCP/IP model is application, transport, network, data link, and physical. The TCP/IP model shows the more common terms and layers used when people talk about TCP/IP today. The bottom layer focuses on how to transmit data over each individual link. The data link layer focuses on sending data over one type of physical link. For instance, networks use different data links protocols for Ethernet LANs versus wireless LANs. The network layers focus on delivering data over the Ether path from the original sending computer to the final destination computer, and the top two layers focus more on the application that need to send and reverse data. Note: a slight difference for layer original versions of the TCP/IP model exists on RFCs 1122, but for mass purpose of both real networking and for today's CCNA, use the 5-layer model shown here in Figure 1.4. Okay, remember the boot layer focuses on how to transmit bytes over each individual links. Okay, the bottom layers is network, data link, and physical. The network layer focuses on delivering data, that's application and transport. Okay, continue. Many of you will have already heard of several TCP/IP protocols, like the examples listed in Table 1.2. Most of the protocols and standards in the table will be explained in more detail as you work through this book. Following in the table, this section takes a closer look at the layers of the TCP/IP model. Okay, in the table 1.2 is the name TCP/IP, architectural model, and example protocols. In the figures column, TCP/IP architecture layers, application, transport, internet, data link, and physical. In the second column, example protocols, HTTP, POP3, SMTP is the architecture layer application. In the transport is TCP, UDP, internet is ACMP, and data link and physical Ethernet 8000.11 or Wi-Fi. Okay, that is the layers and examples of protocols. The every layer in the model TCP/IP. Continue. TCP/IP application layer. Okay, TCP/IP application layer protocols provide service to the application software running on a computer. The application layers does not define the application itself, but it defines service that application need. For example, application protocol HTTP defines how web browsers can pull the content of a web page from a web server. In short, the application layer provides an interface between software running on a computer and the network itself. Probably the most popular TCP/IP application today is the web browser. Many major software vendors either have already changed or are changing their application software to support access from a web browser. And thankfully, using a web browser is easy. You start a web browser on your computer and select a website by typing the name of the website, and the web page appears. Okay, and right now is HTTP overview. What really happens to allow a web page to appear on your web browser? Is a question very interesting. So imagine that Bob opens his browser. His browser has been configured to automatically ask for web servers Larry default's web page or homepage. The general logic looks like uh, the left side is web servers Larry, the right side is web browser Bob. Web browsers Bob say give me your web page, and web server Larry say here is the file home.htm is an example. So what really happens? Bob's initial request actually asked Larry to send his home page back to Bob. Larry's web server software has been configured to know that the default web page is contained in a file called home.htm. Bob receives the file from Larry and displays the content of the file in Bob's web server window. Continue with the topic HTTP protocol mechanisms, taking a closer look. This example shows how application on each endpoint computer, specific the web browser application and web server application. These use TCP/IP application layer protocol. To make the request for a web page and return the content of the web page, the application uses the Hypertext Transfer Protocol (HTTP). HTTP did not exist until Tim Berners-Lee created the first web browser and web server in the early 1990s. Berners-Lee gave HTTP functionality to ask for the content of web page, specific by giving the web browser the ability to request files from the server and giving the server a way to return the content of these files. The overall logical matches was shown in the figure 1.5 and figure 1.6 shows the same media but with details specific to HTTP. Is a little note, the full version of most web address, also called Uniform Resource Locators (URL) or Universal Resource Identifiers (URI), begins with the letters HTTP, which means that HTTP used to transfer the web page. So the same example. In the left side is web server Larry, in the right side is web browser Bob. In the step 1, web browser Bob sending a HTTP header into inside of the HTTP header have gethome.html is as get, and the left side web server Larry return HTTP header OK with datahome.html is a response. This is the step 2, and more. One moment later, see no 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 is delivery the more data the file or home.html is HTTP GET request, HTTP reply, and one data only message. So to get the web page from Larry and step 1, both sends a message with a HTTP header. Generally, protocols use headers as a place to put information used by that protocol. This HTTP header includes the request to get a file. The request typically contains the names of the file, home.html in this case, or if not, field names is mentioned. The web server assumes that both wants the default web page. In the step 2, shows the response from the web server's Larry. The message begins with a HTTP header with a return code 200, which means something as simple as OK, returning the header. HTTP also defines other return codes so that the servers tell the browser whether the request worked. Here is another example. If you ever look for a web page that was not found and the receiver an HTTP 404 not found error, you receive an HTTP return code of 404. The second message also includes the first part of the request file. Is an example. In step 3 in figure shows another message from the web server's Larry to web browser's Bob, but this time without an HTTP header. HTTP header transfers the data by sending multiple messages, each with a part of the file. Rather than wasting space by sending repeat HTTP headers that list the same information, this additional message simply omit the header. Only in the first message contain the header of HTTP. In the second message only send information of the data page is an example. And the next topic, HTTP AP transport layer. Although many HTTP application layer protocols exist, the TCP AP transport layer includes a smaller number of protocols. The two most commonly used transport layers protocols are the Transmission Control Protocol (TCP) and the User Datagram Protocol (UDP). Transport layer protocols provide service to the application layer protocols that reside one layer higher in the TCP/IP model, although a transport layer protocol provides a service to a high layer protocol. This section includes that generally concepts by focusing on single service provided by TCP. Error recovery. The CCNA official circuit introduced to TCP/IP transport and application. So, in the topic TCP error recovery basics, okay, to appreciate what the transport layer protocol do, you must think about the layer above the transport layer, the application layer. Why? Well, each layer provides a service to the layer above it like the error recovery service provided to application layer protocols by TCP. For example, in Figure 1.5, Bob and Larry use HTTP to transfer the home page from web server Larry to Bob's web browser. But what would have happened in Bob's HTTP GET request had been lost in transmitting through the TCP/IP network. Or what would have happened if Larry response, which include the contents of the home page, had been lost? Well, as you might expect, in each case, the page would not have shown up in both browser. TCP/IP needs a mechanism to guarantee delivery of the data across a network, because many application layer protocols probably want a way to guarantee delivery of data across a network. The creators of TCP included an error recovery feature. The recovery from error, TCP used the concept of acknowledgements by 17 outlines the basic idea behind how TCP notices lost data and asks the sender to try again. In the same example, the Larry web server is the side left and the web browser Bob is the side right. In the first step, start with the left side. TCP sec equal 1 with HTTP awk and data web page sent to web browser. And the second packet, TCP sec equal 2 and more data, more web page. In this case, lost these two packets. And the next time, send TCP sequence equal 3, more data rest of the page web. In this case, web Larry server sends packet 1, packet 2, and packet 3, but web browsers both only receive packet 1 and packet 3. The packet 2 is lost, and then web browser both send to next. I don't have a second packet. Is TCP error recovery service as provided to HTTP. And this figure shows web browser Larry sending a web page to web browser Bob using 3 separated messages. Note that this figure shows the same HTTP headers as figure 1.6, but it also shows a TCP headers. The TCP header shows a sequence number, sec, with each message. In this example, the network has a problem, and the network fails to deliver the TCP message, called a segment with a sequence number 2. When both receive message with sequence number 1 and 3, but does not receive a message with sequence number 2, both realize that a message 2 was lost. That relation realization by Bob's TCP logical cause Bob to send a TCP segment back to Larry, asking Larry to send message 2 again. In topic send layer and adjacent layer interactions is another topics in this section. Figure 1.7 also demonstrates a function called adjacent layers interaction, which refers to the concept of how adjacent layers in a network model on the same computer work together. In this example, the high layer protocol HTTP wants error recovery, so it uses the next lower layer protocol TCP to perform the service of error recovery. The lower layer provides a service to the layer above it. Figure 1.7 also shows an example of a similar functionality called same layer interaction. When a particular layer one computer wants to communicate with the same layer on another computer. repeat this very important this question. In the demonstration, a function called adjacent layer interaction, which refers to the concepts of how adjacent layers in a network model on the same computer works together. In this example, the height layer protocol is HTTP wants error recovery. So it uses the next lower layer protocol, the TCP, to perform the service of error recovery. The lower layer provides a service to the layer above it. In the top is HTTP, below is TCP. Also shows an example of similar functions called same layer interaction. Is adjacent layer and same layer interactions. When a particular layer one computer wants to communicate with the same layer on another computer, the two computers use headers to hold the information that they want to communicate. For example, Larry sets the sequence number to 1, 2, and 3 so that board could notice when some of the data did not arrive. Larry's TCP process creates the TCP headers with the sequence number. Bob's TCP process receives and recreate to the TCP segment. Table 1.3 summarizes the key points above how adjacent layers work together on a single computer and how one layer on one computer works with the same networking layer on another computer. Okay, in the first column concept, same layer interaction on different computers is very important. This definition, same layer and adjacent layer interactions concept, same layer interaction on different computers. Description: the two computers use a protocol to communicate with the same layer on another computer. The protocol defines a header that communicates what each computer wants to do. In the concept, adjacent layers interaction on the same computer. In the description, on a single computer, one lower layer provides a server to the layer used above. The software or hardware that implements the higher layer request as the next lower layer perform the needed functions is easy to learning. In the same layer, I need two computers, and adjacent layers is in the only computers. Okay, in the topic TCP IP network layer, the application layer includes many protocols. The transport layers include fewer protocols, most notably TCP and UDP. Is this in the layer network? TCP and UDP. The TCP/IP network layer includes a small number of protocols, but only one major protocol, the Internet Protocol IP. In fact, the name TCP/IP is simply the names of the two most common protocols, TCP and IP, separated by a slash. AP provides several features, most importantly addressing and routing. This section begins by comparing AP's addressing and routing with another commonly known system that uses addressing and routing, the Postal service. Following that, this section introducing the IP addressing and routing. More details following in the chapter 3 with the fundamentals of WANs and IP routing. So, Internet Protocol and the Postal Service is a comparison for introduction to the AP. Is example: imagine that you just wrote two letters, one to a friend on the other side of the country and one to a friend on the other side of a town. You address the envelopes and put on the stamps, so both are ready to give in the postal service. Is there much difference is how you did each letter? Not really, typically. You used to one put them in the same mailbox and expect the postal service to deliver both layers. The postal service, however, must think about each letter separately and then make decisions of where to send each letter so that is delivered. For the letter sent across town, the people in the local post office probably just need to put the letter on another truck. For the letter that needs to go across the country, the postal service sends the letter to another post office, and then another, and so on, until the letter gets delivered across the country at each post office. The postal service must process the letter and choose where to send it next. To make this work, the postal service has regular routes for small trucks, large trucks, planes, boats, and so on, to move letters between postal service sites. The service must be able to receive and forward the letters, and it must make good decisions about where to send each letter next, as shown in the figure. In the figure is the local area postal service in California or only across the town. Still think about the postal service. Consider the difference between the person sending the letter and the work that the postal service does. The person sending the letter expects that the postal service will deliver the letters most of the time. However, the person sending the letter does not need knows the details of exactly what path the letters take. In contrast, the postal service does not create the letter, but it accepts the letter from the customs. Then, the postal service must know the details about address and postal codes that group addresses into large groups, and it must have the ability to deliver the letters. The TCP/IP application and transport layers act like the person sending letters through the postal service. The super layers works the same way regardless of whether the endpoint host computer are on the same LAN or area separated by the internet. To send a message, the super layer asks the layer below them, the network layer, to deliver the message. The lower layers of the TCP/IP model act more like the postal service to deliver those messages to the correct destination. To do so, the lower layer must understand the underlying physical network because they must choose how to best deliver the data from the one host to another. So, when does this make it a network? Well, the network layer of the TCP/IP networking model, primarily defined by the Internet Protocol (IP), work much like the postal service. IP defines that each host computer should have a different IP address, just as the postal service defines addressing that allows unique address for each house, apartment, and business. Similarly, IP defines the process of routing so that the device called routers can work like the postal office, forwarding packets of data so that they are delivered to the correct destination. Just as the postal service creates the necessary infrastructure to deliver letters, post office, sorting machines, trucks, planes, and persons. The network layer defines the details of how a network infrastructure should be created so that the network can deliver the data to all computers in the network. In the same topic, Internet Protocol addressing basics, AP defines address for several important reasons. First, each device that uses TCP/IP, each TCP/IP host needs a unique address so that it can be identified in the network. AP also defines how to group